Okay, today we're going to look at quiz 4 from Organic Chemistry 2 from spring of 2019. And quiz 4 is basically a review of chapters 11 and 12 and 14. 11 and 14. And so let's take a look at page 1 here with these questions and see if we can fill in some of these blanks. So up at the top, we have an alkene going to an epoxide. There's a couple different ways of doing that. Right? The simplest is MCPBA. Right? We could also use hydrogen peroxide and sodium hydroxide, but MCPBA seems just fine for us. And then we've got a couple options here at the end. We want to make a trans diol. Right? That means we're basically doing a ring opening from our epoxide. And the simplest way that we can do that here is, oops, I meant to be a plus there, right? H3O plus. Although I guess in theory you could have done sodium hydroxide and water too and done a base ring opening of the epoxide, but aqueous acid seems to be a good choice in this case. Okay, so pretty simple, pretty straightforward. Alkene to an epoxide, epoxide to a trans diol. Now we got something here a little bit weird. So we've got a, let me get a different color here, right? So we've got a tertiary leaving group, right? We've got a bromine on a tertiary group, right? And then in our product, right, it looks like we scrambled our stereochemistry. Now remember, if we're scrambling our stereochemistry, that means we have to go through some kind of cationic intermediate, right? So likely what's going to happen is we're going to do a substitution, right? We're going to do a substitution. Right, we're doing a substitution because we're swapping a leaving group for an incoming group. So a halide, and we're swapping a halide for an ether, right? A halide for an ether. That didn't look quite as neat as I wanted it, so halide to an ether. Okay, so we're doing a substitution, swapping a halide for an ether. We're at a tertiary carbon, right? And we scramble the stereochemistry. All right. So all this kind of adds up as evidence that we are going to be doing an SN1 type substitution. Okay, and if we're doing an SN1 type substitution, let's pick blue here. If we're doing an SN1 type substitution, we need weak base, right? Weak base, weak nucleophile, right? And a weak base and a weak nucleophile that swaps a halide for an ether, that is simply an alcohol, right? That is simply an alcohol. So all we're going to do is cleave our bond right there, right? We're going to cleave our bond right there and turn that into an alcohol instead, and then we add in the rest of our stuff, okay? So all this stuff over here, we're kind of, analyzing what we need before we even try and write something down, okay? So spend some time thinking about what the reaction is showing you, the implications, and what you might remember from your flashcards or however you memorize this. All right, getting to the ones that are a little bit more complex here now. So we start out with a cis methyl, alcohol over here. And we end up over here with a trans methyl thiol. So if we're specifying stereochemistry, we know we can't go through a carbocation intermediate, right? We can't go through a carbocation intermediate. Otherwise, it's going to rearrange, it's going to shift, it's going to scramble stereochemistry. So we know, right, if we're looking here in green, we need to do a substitution. Right, we need to do a substitution for an alcohol to a thiol. And we need to invert stereochemistry. Right, we need to invert stereochemistry along the way. Now this right here, that is basically saying, hey, we need to do an SN2, right? We need to do an SN2 reaction. Now here's the problem. there is nothing that we know that can directly substitute an alcohol for anything, right? Alcohols have to be made to leave in some way, usually through the form of some kind of acid, okay? But remember, if we use something like, a generic Bronsted acid, we're going to end up forming a carbocation, right? If we use a Bronsted acid, we're going to end up forming a carbocation, and then we're going to end up scrambling and rearranging, and we won't get the product that we want. So there is something else. There is a substitution that we can use, or excuse me, there is a reaction we can use to substitute an alcohol for something. And to do that, we're going to use our tosylate, right? So tosyl chloride. So if we use tosyl chloride in the presence of a pyridine, I should say, then what we will end up doing is turning our alcohol into our tosylate group, right? Which we just abbreviate by OTS. Now, OTS, right, our tosylate is a very good leaving group. It is a stable leaving group, right? It's not like if we used a Bronsted acid where we'd protonate the alcohol and make water and it would kick off, right? We can isolate this tosylate intermediate, right? And so that's the usefulness of this. Let's use black here then. So now, right, now we need to swap our tosylate, right? Now we need to do a tosylate for a thiol, and we need to do an SN2 reaction, right? So for that we need a good nucleophile, right? We need a good nucleophile. Right? So we need a good nucleophile, which for us is going to mean, right, our sulfur with alone pairs and negative charge. But that's not a thing, so let's balance out our charge, right? Let's use sodium. Let's put a sodium salt in there, okay? And there we go. That seems reasonable for us, right? We don't have to worry too much about shouldn't have to worry too much about our solvent in this case. Right? We could pick something like, well, I don't know, THF maybe will be all right, or DMSO, something like that, okay? So remember, going back over here, sorry about that. Right, going back over here, right, we can't directly substitute an alcohol for anything, right? We have to use some kind of acid to protonate it to make it want to leave, or we can go through the tosylate route, which we can isolate as a separate product and then do something else with that, okay? All right, question on the bottom. We've got an alcohol, we got sulfuric acid. Remember, there was a slight typo here. There should have been a 4 there. It kind of got scrambled down to the last row there. I don't know what happened. But anyway, sulfuric acid, high heat, alcohol, acid catalyzed dehydration. Okay? So once you make the alkene, now it's asking us to make a cis-diol. Well, there's a couple ways we can do this. The most straightforward way is to use osmium tetroxide. Or we could also do KMnO4. Right, we put it into some hydroxide in water and keep it cold. That would be an adequate way of making this too, although, as we will learn, KMnO4 is not really an ideal choice, but so far for what we know, it's okay. There we go. I'm going to zoom out. That way we have everything here. And then we will move on to the last page where we got a mechanism. All right, and it says propose a mechanism for the following transformation. Okay, so I'm just going to abbreviate this as H plus to keep things a little bit simpler here in our mechanism. All right, we've got an epoxide, we've got a generic aqueous acid. Protonation is going to be our first step. Okay, so let me get this drawn out here. Okay. So we've got our protonated epoxide. So now something's going to want to come in and pop open that ring. Now remember, since we're going acid catalyzed ring opening of an epoxide, right? Whatever the incoming group is going to hit the most substituted carbon, or is going to hit the most stable partial positive that gets left behind, right? And what I mean is this. We've got green and we've got purple there, okay? We've got green, we've got purple. Remember, with a ring opening for an epoxide under acidic conditions, that oxygen is going to be wanting to break one of those bonds. It's going to want to break one of those bonds either to the green or to the purple. And it's going to want to break the bond to where it leaves behind the most stable carbocation. So what's going to happen is our pi bond is going to come in, hit our most stable partial positive there, right, and then do a ring opening. Now what I'm going to do is copy this, so I don't have to draw the whole thing over again. And then I'm going to fill in our mechanistic arrows here. Alright, so let me draw what happened. So following our green arrows over there, right, we made that bond. Right, we made that bond. Whoops, that should be in blue over here. And we have our alcohol over here. And we left behind a positive charge, right? We took a bond away from that from that red carbon there, right, and left behind a partial positive. So now we're going to swing open over here. Right, that pi bond is going to swing over. I'm going to duplicate again here. Right, and then I'm going to draw what happened, the consequences of our actions, right? Oops, that didn't turn out very nice. There it is, okay? And now we've left our positive over here. Let's bring in some water now to make our alkene like we have at the end over there. And this will take us to our product there, okay? Let me zoom out and show you guys. So a couple things to remember on this mechanism, right? When we're opening an epoxide under acidic conditions, we don't completely break that epoxide, right? Something comes in and breaks it open, but the incoming group hits the most stable carbon where a partial positive would be left behind, right? Usually it's the most substituted, right? But we need to pay attention to stability of a positive charge. Okay. And there it is. So that's all we have for quiz 4.